Okay, welcome everyone. Thank you for joining us RecSys 2020 session on Real-World Applications 2. I'm Dr. Weike from Shenzhen University, China. I'm your session chair. In case of some emergency, we have a secondary session chair, Dr. Zhenhua from Huawei. Thanks the organizer for such a thoughtful arrangement, and thanks Zhenhua for being the secondary session chair for our session. In this session, we will have 6 presentations, 4 of long papers and 2 of industry talks. If you have any questions, please go to Coba and post your questions on the specific paper page. Okay, let's get started. Our first speaker is Dr. Pigi Kouki. She is a senior data scientist at RelationalAI. Her talk is From the Lab to Production, a case study of session-based recommendation in the home improvement domain. Let's welcome Pigi.
Thank you. Can you see my screen?
Yes, we can see.
Okay. Hi everyone, and thank you for attending my talk. Today I will present our paper on session-based recommendations for the home improvement domain. This is joint work with my colleagues from RelationalAI, the Home Depot, and HyperCube. Our work is motivated by 2 different lines of research. In the first case, there is a multitude of algorithms for session-based recommendations. These algorithms range from simple k-nearest neighbor approaches to complex deep learning architectures. However, the evaluation of these models is based on offline evaluation metrics only and is using different datasets. At the same time, very recent research showed that baseline models, when carefully tuned, can outperform deep learning ones in a variety of metrics. In the second line of research, there is a lot of discussion around the fact that offline evaluation is not enough. This is especially true for the home improvement domain, for the following reason. Offline evaluation penalizes an algorithm if the recommended product is not exactly the same with the product in the ground truth. However, it is usually the case that there are near identical products that they should be considered as equally good recommendations, even if they do not share the same product identifier. Let's give an example to showcase this shortcoming of offline evaluation metrics. Assume that there is a user that has a fridge and a dishwasher in the cart, and we know from historical data that the item added to the cart next is a microwave. Also assume that 3 different algorithms came up with 3 different recommendations. Algorithm A recommended a microwave that is very similar to the microwave added to the cart. Algorithm B recommended a kitchen stove, and algorithm C recommended a kitchen sink part. For a human, when looking at these recommendations, it is very simple to understand that there are different levels of relevancy. Recommendation of algorithm A is more relevant compared to the recommendation of algorithm C, which is more relevant compared to the recommendation of algorithm C. However, when applying traditional evaluation metrics, all these recommendations will be considered as equally bad, since none of the IDs here matches the ID in the ground truth. So, given the above discussion, when it comes to a large e-commerce application such as the Home Depot, it is not straightforward to know what is the best session-based recommendation algorithm to put into production. First, because there are so many models that we can choose from, and second, because the offline evaluation alone is not enough to make an informed decision given the peculiarities of the domain. In this paper, we describe the journey of the Home Depot towards finding the best session-based recommendation algorithm. Our evaluation is divided into 3 parts. In the first part, we evaluate the performance of 14 different models in a variety of metrics and distinguish the best 5. In the second part, we use those 5 models and perform an additional round of evaluation using human experts to account for different levels of relevancy. In the third part, we use the best model from the previous part and perform an A/B test that showcases the improvement in business metrics that the Home Depot was able to get as a result of this work. Now let's discuss the different parts, starting with the offline evaluation. We evaluated the performance of 14 different models designed for session-based recommendations. 8 of them were baselines, and 6 were deep learning architectures. We report the performance of each model in a variety of metrics, ranging from metrics that evaluate the ability of the model to predict the immediate next item or a list of items. We also report results for coverage and popularity. We retrieved add-to-cart actions for products belonging in 3 datasets that get a lot of traffic in the Home Depot: outdoors, tools, and appliances. For all models, we performed hyperparameter tuning using a validation set. Here, we will present a subset of the results of the offline evaluation. The graph here shows the performance of the 14 models for the outdoors category in terms of predicting a list of items and in particular precision at 5. For this metric, a baseline model called VSTAN statistically outperforms all other models, including the deep learning ones. When evaluating the ability of the models to predict the immediate next item, here we report hit rate at 5, then a very recent graph neural network model called SRGNN is the best option. And finally, when it comes to coverage and popularity, VSKNN, a baseline model, and GRU4Egg, a deep learning model, seem to be the best options. The results of this offline evaluation is that not a single model outperforms all others in all accuracy metrics. So we selected the 5 models that perform the best to participate to the second round of evaluation. In the second part of the study, we trained all 5 models using the same data and generated predictions for the same real sessions. Then, we asked human experts from the in-house validation team of the Home Depot to give us labels. Now let's discuss the design of the experiment. Validators were shown 2 sets. The first set consisted of the items that the user has in the cart, and these were the items that each of the 5 models used in order to come up with predictions. The second set showed the items that the user added additionally to the cart, which was considered as our ground truth. Then, we provided with a set of 5 recommendations for each of the 5 algorithms. For each recommendation, we asked the validators to give 1 out of 3 available labels: thumbs up, check, and thumbs down. A recommendation was considered as thumbs up, which we call objective relevant, if the recommended item was exactly the same or very similar to the item added to the cart. In this example, the says long here is very similar to the says long of the ground truth, so despite the fact that the 2 products do not share the same ID, the recommendation is considered as objective relevant. A check, which we call subjective relevant, was assigned to recommendations that were not objective relevant. However, they made sense given the items currently in the cart. Sorry, can someone mute? Thank you. For example, an ottoman is not in the items that will be added to the cart next. However, given the fact that the user has added to the cart a swivel, it makes sense for the recommender system to recommend an ottoman. Finally, recommendations that were irrelevant to the items currently in the cart and items in the ground truth were assigned the thumbs down label. For each recommendation, we got labels from at least 3 different validators. Since we asked the validators to use their critical thinking, there were times with disagreement. To resolve for disagreements, we applied a simple majority vote algorithm. This was a large experiment. We got around 35,000 labels for around 1,000 sessions. Here are the results for the objective relevant metric for all categories. The model that statistically significantly outperformed all others is GRU4Egg. An interesting note here is that we chose this model to participate in this part 2 of the evaluation, not because of the great performance in terms of accuracy metrics, but because of its great performance in terms of coverage and popularity. The results of the subjective relevant metrics show that another deep learning model, STAMP, outperforms all others. Again, STAMP was chosen to participate in this part 2, not because it performed very well in accuracy, but because it performed decently enough in accuracy, and at the same time it showed satisfactory performance in terms of coverage and popularity. In this slide, we compare the performance of the algorithms in part 1 and part 2 of the study. To this end, we plot the precision at 5 from part 1, along with the objective relevant metric from part 2. The conclusion is that the ranking of the algorithms from the offline evaluation does not agree with the ranking of the algorithms from the human evaluation. For example, VSTAN, that was the clear winner in the offline evaluation in this metric, ranked the last in the objective relevant metric in 2 out of 3 datasets. If we look closer to the comparison between baseline models and deep learning architectures, we observed that the baseline models ranked in the last positions, suggesting that for the home improvement domain, deep learning models seem to be more appropriate because they can probably capture deep interactions between the items that simple methods are not able to do. Finally, in this graph, we plot the percentage of recommendations that were assigned a label thumbs up by the validators. However, the ID of the recommended product did not match the ID of the product in the ground truth. This happened with the example of the saislong we described a few slides ago. In other words, this percentage shows how often an item should be considered as relevant because it is very similar to the ground truth. However, an offline evaluation metric cannot capture this fact because it needs exact match between the recommended and the ground truth item. Interestingly, this percentage is very high for all algorithms. It ranges from 6 to 21%. This shows that offline evaluation metrics cannot capture a very large number of recommendations that are indeed very relevant and very close to the ground truth. As a result of this second part of the study, we had to choose only one model to move to the A/B test. We decided to go with STAMP since it performed the best when summing the scores for objective and subjective relevance in 2 out of 3 datasets. So let's discuss the design and results of the A/B test. The treatment was the STAMP model, while the control was a third-party leading solution that the Home Depot has in production. We ran the A/B test for 2 weeks with 50-50 split in the full traffic. The results are as follows. Conversion rate increased by 15.6% and revenue per visit increased by 18.5%. Both differences are considered statistically significant. To summarize, in this work, we studied the performance of a set of models for session-based recommendations for the home improvement domain and performed 3 different evaluation procedures. We hope that our lessons learned towards finding the best session-based recommendation algorithm for our application scenario can be helpful to researchers in industrial and academic settings. Finally, we would like to note that our findings showed one more time that offline evaluation is not enough in the session-based recommendation scenario. An important lesson learned is that experiments with real users are needed to better understand how its method performs. Thank you very much, and please let me know if you have any questions. You are on mute, we cannot hear you. We cannot hear you, you are on mute.
Sorry. Okay. There are more than 10 methods in your study. The first question is whether have you studied the complementarity between 2 or more methods for the studied problem? I mean, hybrid solution or ensemble solution will be better or not?
Yes, this is a good question. So we expect that an ensembling method would outperform single methods because its method has different strengths and differences. But in this study, since we wanted to put the model into production, it was already very difficult to put a deep learning architecture into production, and we did not want to make it even more complex. But since we observed this difference both in the offline evaluation and the human experts, in our future work, we plan to experiment with ensembling the methods.
Okay, I see. The second question is a live question. For all the methods or models, their input are the same, right?
Yes.
Okay. And another one is there some disagreement between human and I think human experts are the same, right? Human and experts. They are the same,
yes,
right?
They are human experts. Yes, it's the same, and we have different human experts validate the same recommendation given the same context. And again, since we asked the validators to use their critical thinking, there was disagreement. So we applied the majority vote algorithm, and when there was no disagreement between the annotators, we did not use these labels for our results. We throw them away.
There's no live question. I have another one. when I read your paper, I recall there is a branch in machine learning called structured prediction. That is, we will, for example, in your case, we will consider the taxonomy of the items or the products. For example, two items are similar or not, they are in different nodes in a tree or in a taxonomy. So probably that will be address the similarity issue. Two items are similar, and so the ID is different. We may also consider they are relevant. Structural prediction. Have you considered this?
In this work, no, but this is a very good comment. So in our future work, we plan to use these labels in order to automate the process of understanding if a recommendation is very close to the actual ground truth item, and we plan to use the taxonomy of the product and other information such as the text or description of the product.
Right. Okay. It's interesting. Due to time limitation, let's thank Pigi again and move to the next presentation. Thank you. The next speaker is Symeonidis. Unfortunately, he is not online yet, so we will play his recorded video. Okay.
Hi everyone, thank you for being virtually here for the presentation of my work done during my research master in collaboration with my supervisor Daniela Louise and Simon Blanchard. So the title of our paper is a bit long, but Diane can summarize the topic we'll discuss here, which is seat recommendation at reserved seating venues. So our problem is the following. When a customer buys a ticket in a venue in a theater such as the Saint-Denis theater represented here, what location will he choose? So let's start by a summary of what drives the customer in his decision. The first observation that can be made is that the choice will depend on the location of the seat in the room. For example, some people might prefer to sit in the front rather than the back or in the center of the room, etc. And so among the factors to consider, the position of the seat in the room is essential. But that's not all. As over time the room fills up, some seats have to be updated to become occupied, and also the seats that are still available may become less attractive if they are surrounded by unavailable seats. And therefore, proximity to others is also a factor to consider. So finally, one thing that also can be said is that all these preferences are personal, and the importance of these factors can be very heterogeneous from one customer to another. So yeah, and based on this remark, how can we model our problem? So two different points of view are possible. And the first one is the traditional classification approach. So we have partially filled room for inputs, and the class here are the available seats. And so we use a classification algorithm to find which ones are the most attractive. And so doing so allow the exploitation of data from all customers to model high order interaction with an algorithm that will have a high capacity, for example, with neural networks. But on the other end, customers are not distinguished, and the information of each behavior will be lost because the data of all customers is concatenated, which can be a weakness here. And so on the contrary, the second solution is to treat each customer individually and thus make a recommender system, what we can call the recommender system. Doing so allows the capture of differences in behavior, but individual level modeling performance also tend to suffer when customer data is sparse when you have only a few or no past purchase, which is the borderline case. And so the core start problem for customers without history is also a weakness. So which one of the 2 points of view is the best here? Is it the one that process all the data together or the one that distinguish each customer? In this paper, we argue that the 2 approaches are complementary in the information provided for the prediction. The first one can focus on high-order interaction between seats, while the second one only use one customer history to consider personal preferences. And so combining them allows us to be more flexible for a customer for which the model's user has little to no data. So here's a diagram representing the overall architecture of our approach. So from a database of ticket purchase data from one or more rooms, we apply preprocessing to have it in the format we want. And then the architecture is divided too, with an individual level part, which is represented here in the upper part, which is calculated for each customer separately if we have enough data. So here we write if we have more than 5 choices, but 5 is an hyperparameter. And the deep part in the lower part of our diagram, which is computed without any customer distinction and can use all the data. And so these 2 methods provide 2 different seed prediction, which are then merged to obtain our final prediction. So let's successively describe the individual level part and the deep one before looking at how we combine them. First of all, the individual level parts, which is here a choice-based model with estimation by machine learning. So there's 3 steps for the computation. The first one is for each seat J in every room where customer I chooses a seat. We compute a set of feature Fij based on all the factors like position, proximity to others, etc. Then the second step is to introduce Yij, which is a binary variable that indicates if the customer I actually chose the seat J. And finally, the first step is to train a binary classification model to estimate the probability Pyj that the seat J is chosen by customer I. And so various algorithms can be tried here, like support vector machine, random forest, or gradient boosted trees. So that's it for the individual level component. For the deep one, here we have all the aggregated data, and therefore we can use an architecture that requires more data. And the problem here is seen from a multi-class classification point of view, with 1 seat per class, and the room is given as input in the form of a binary image, which keeps the geometry. And thus, the architecture we use here is a CNN, but with 2 adaptations. The first one is due to the fact that the number of class, which is the number of seats, is the same size as the input, which means that it can be seen as the reconstruction of the input. And thus, the architecture we choose is similar to a CNN, but autoencoder. And the second modification is made to make the prediction only on the available seats and to assign a 0 probability to the occupied ones. And it is done by applying a mask on the softmax output of the network. So for the combination now, it was important to do it differently for each customer because the performance of the model varied significantly. For example, the individual level component performed much less well with a small history. And even considering customer with the same history size, some were much more predictable than others. And so we proceed to a convex combination of the two output vector with alpha here learned for each customer by gradient descent. And the sigmoid function is also applied before the gradient computation to avoid any problem of exploiting gradients. So 2 experiments have been conducted to validate our approach. In the first one, we use data from a work conducted by Blanchard et al., who have collected choices of participants from panel. So several datasets are created with different configuration, so with varying room size, number of choices made per client, but also room occupancy, etc. And so all the details of the result are obviously in the paper, but one main thing to remember is that the hybrid architecture outperform all other methods, and in particular, its 2 components used alone, which gives evidence that the 2 components provide useful and complementary information for prediction. For the second experiment, we obtained 12 years of ticket purchase data from a large North American concert hall. The room is represented here. Using data from a real room added challenges like not having the same history size for all customer. But again, the hybrid architecture provides the best performance for prediction, which prove the flexibility of the model from the quantity of data available and also from the size of the room. So to conclude, we provide a solution to a problem that has been very little addressed in the past, whereas it could be used by the cultural industry to improve marketing strategies with revenue management or with personalized recommendation. This solution is a hybrid method for recommending seats, and it's the state of the art by being more flexible on the amount of data available. And the results are confirmed with a real-world application, which is also a contribution. And yeah, that's it. Thank you for your listening.
Okay, thank you. Thank you, George, for playing the backup video for us. We may leave questions on Coba if we have any. Actually, I also have 2 questions, and we'll post them on Coba. And now let's move to the third presentation. Our third speaker is Jesus Homer Alvarez Markus. He is a PhD student at the University of Duisburg-Essen. His talk is In-Store Augmented Reality-Enabled Product Comparison and Recommendation. Let's welcome Omar.
Hello, thank you for the introduction. Yes, again, my name is Jesus Alvarez. I am part of the Interactive Systems Group at the University of Duisburg-Essen, and I am here to present our research regarding in-store AR-enabled product comparison and recommendation. Nowadays, it is not uncommon for specialized stores to have plenty of different options for products of the same type. This can quickly become an issue if the client lacks the required knowledge for choosing one, and if we also consider that customers not always have well-defined preferences, they may suffer of choice overload and being capable of making a decision with confidence. We know that recommender systems are suitable tools for addressing these issues. The problem is that they are mostly an online element, and especially in shopping scenarios, they rely heavily in many other online features, which could hardly be transposed into physical settings, or so was the case some years ago. Now that multi-channel retailing is a thing, and the different customer touchpoints are more and more integrated, physical retailing is slowly evolving into a new kind of experience, and special attention must be paid to augmented reality technology, which allows for the seamless integration of digital and physical worlds. Combining it with recommender systems has the potential for offering both an engaging customer experience and pragmatic benefits in terms of search and decision support. And in this case, we would be also combining physical and online retailing, which means that we can have the benefits of both worlds too. This constitutes the foundation of our approach to AI-based recommending at the point of sale. Now, I will go through the main points of our concept and the implemented prototype that is based on it, which runs under Microsoft HoloLens and takes vacuum cleaners as the product domain. In our approach, the information appears anchored to the physical product. Hopefully, you can see now the prototype running in our lab. The part on the right side is for recommendations, but we'll leave that for later. The left side shows various categories and how well the product performs for each one of them. Tapping on a category grants access to the related attributes, and tapping on an attribute shows other related properties, its location in the product, and a description. The second point of our approach has to do with supporting attribute comparison, which is the most common practice when deciding between different products in a physical store. However, it has limitations concerning short-term memory demands, but luckily previous research indicates that they can be alleviated by using augmented reality. In the prototype, users can select different products by tapping on them. So a color is assigned to each selected product. In this case, that's purple for this one. When we move to another product, we can see which ones have been previously selected. And if we select another one, the system will display their attributes in a side-by-side manner. We can do so with up to 3 products. The functionality presented in the previous point is still available, so that it is possible to go inside categories and obtain more information. The method allows clients to move around and compare products that are far away one from each other. The recommendation part is built on top of this. The system provides recommendations for each physical product. It uses a content-based technique which utilizes the attributes of the product currently in the user's AI focus for retrieving similar items. 2 similarity scores are calculated. The first one takes into account functional attributes only, while the second one is based on visual aspect. It has 2 components, one that takes visual-related attributes for its calculation, such as color or size, and another one that is based on image similarity. Both are combined to obtain the similarity score for the appearance. Finally, the system provides 4 recommendations, 2 of them for each similarity score. In the prototype, we can see how they are presented. The client can examine them, which is what the user is doing now. They can be removed, which brings a new item on its place. They can also be saved by using the heart icon, or we can compare them just as we would do with a physical one. Regarding this, a recommendation can contain products that are physically present at the store, as well as others that are only digitally available. Lastly, attributes can be critiqued by users, which in turn generates new recommendations. This is done by tapping on these 2 little buttons that appear next to a selected attribute, in this case for requesting items with a higher or lower weight than this one. Then a new rule is added and the recommended items are refreshed. This is not the first attempt at AI-based shopping support or in-store recommendations, and there are even a few instances where they have been combined already, like it is the case for Gutierrez et al. However, research in the area is still scarce and requires further exploration. Aspects such as the development of the client's preferences in this context, or the implications that having both physical and digital products may have in the client's decision-making process, are factors that have been generally overlooked due to how rarely these elements are presented together. We can extract our research questions from these concerns. That is, how effective are product recommendations provided through augmented reality? How can the development of the user's preferences be supported by AR-enhanced product displays? And does the presence of a physical product serve as a cognitive anchor for selecting among online products? To address these questions, we have performed a small user study that unfortunately had to be limited in size and scope due to physical proximity being restricted because of the COVID-19 pandemic. In any case, 10 participants took part in it, 9 of them with a strong technical background. 3 real vacuum cleaners were used, together with a database with 100 other products for generating recommendations. Participants were first introduced to the system, and then they were asked to solve 2 scenarios where they were given several requirements and had to find a suitable vacuum cleaner. The final choice could either be one of the physically present products or an item found by using the recommending functionality. Participants had to fill a 3-item long questionnaire between tasks addressing their final decision and the relevance of the presence of physical items. And by the end of the session, they also answered the rescue items by Pu et al. And some other system-related questions. Jumping directly into the results, the rescue items were rated positively in general, particularly those regarding the novelty and diversity of the recommendations, the ease of use of the system, and the use intention, while the explanation of the recommendations seemed to be the system's biggest flaw. For the system-related items, the highest scores were given to the preference of the system over a more traditional medium and use intention, but the novelty of using a head-mounted display may have had an impact on these results. Closely behind are the items that deal with the helpfulness of physical products, while attribute exploration seemed to be the main issue for most users. The results of the Between Tasks questionnaire reinforce the helpfulness of physical products during the process, and even if not with that conviction, participants also showed confidence in the final choice to fulfill the given criteria. The empirical data shows that even though users were quicker in solving the second task, features like critiquing, selecting attributes, and reading their descriptions were used more often too, suggesting that they were found useful to accomplish the given tasks. However, it also indicates a learning factor, supported by most participants affirming that they felt able to use the system competently only after having completed the first task. With respect to how users made a final choice, when solving a task, all participants focused on some physical products and their recommendations, while completely ignoring those physical ones that they thought were not suitable. And by doing so, participants seemed to filter the digital space intuitively. Lastly, for both tasks, digital items were chosen way more often than the physical ones, which is interesting because they generally showed confidence in the final choice despite of it. So coming back to our research questions, the recommender system was positively rated and perceived as useful and intuitive. Physical products were regarded as helpful for forming an opinion of the ones available only in digital form. And the selection and exploration of products was influenced by the presence of physical items, which could be a sign of anchoring effects. However, caution is required when interpreting these findings due to the various limitations of the study, such as that participants might not be a representative sample due to their number and technical background. The limited number of physical products, task scenarios also limited the development of user preferences, or the impact that using a head-mounted display may have had in the results. But altogether, we still believe that there is enough evidence to at least consider this to be a viable approach worth to be further explored. Future work will focus on consolidating the results presented here. We also aim to get a deeper understanding of preference construction in a hybrid physical online setting, and to provide more opportunities for users to experience digital products through physical ones. Finally, we would like to study new combinations of appearance and function-based recommendations and how different clients react to them. This concludes my presentation. Thank you very much for listening.
Okay, thank you, Omar. There are no live questions yet. Oh, there are one live question. Would it be easier to use the online shopping recommendation for in-store production recommendation? Since we may have a lot of data online. So would it be easier to using a physical device? Will it be easier?
Instead of using augmented reality? Or what is the question exactly? I mean, the recommended items are already retrieved from an online source, so I don't know if this is what the question.
I think the question is about the scalability of your solution, because for online shopping there will be a lot of products.
Yeah, well, right now we are just using a database with 100 other products for the recommendations, but it could be easily expanded, or it could be an external source as well. So I don't think that's a limitation.
Okay. Okay, I have a question. Very short question. Can we consider the VR solution at VR as a bridge to connect the online and offline shopping, online and offline situations or scenarios? Can we consider it as a bridge to bridge to space
yeah.
online?
Yes, exactly. This is the main idea, so that we can access the features of online shopping when we are doing physical shopping. As it could be an extended catalog, so just with a limited number of products, we have access to the whole product catalog, for instance.
Okay, we still have some time for questions. No live questions coming. Okay, let me ask again. In your slides, I see that there are some real-time feedback, like remove or add to cart. My question is whether your model will be updated on the fly, online, in real time.
Yeah, well, what we've seen right now in the interface is just the recommendations, and what the user can do is that. So, what the user can do is to critique the attributes of the physical product, and that changes the recommended items. So this is
what's. Will it be reflected on the model? I mean, the model will be updated corresponding.
Yes.
Okay. Okay. So, there are no questions. Will the physical device or the VR will it be helpful to improve the interpretability of the recommendation results?
Yes. So one of the flaws of the system is that apparently the users didn't understand why the recommendations were provided to them.
Right.
And right now, the only information that they have is that they are linked to a physical product and that they are modified when an attribute is critiqued, but no other explanation is given. So yeah, that's something that should be improved.
Thank you. So we may continue discussion on the whole platform, and you may look at the questions posted by the audience. Thank you. Thank you, Omar.
Thank you.
Okay, let's move to the fourth presentation. Our fourth speaker is Dr. Panagiotis Symeonidis. He is an assistant professor at the Faculty of Computer Science of the Free University of Bozen-Bolzano, Italy. His talk is recommending the video to watch next, an offline and online evaluation at utv.de. Let's welcome Professor Symeonidis.
Thank you for the introduction. So the paper is the result of our 3-year collaboration with the UTV company, which operates in the province of Alto Adige in North Italy. I want to thank all co-authors, Andreas, Dmitry, Philip, Daniel, Andreas, Ludovik, and Markus for their valuable contribution. So here you can see the outline of our presentation. We will see the motivation of the work, the approach, offline and online experiments, and the lessons learned. UTV is a company that is a platform that supports users to record high-quality German television programs of their choice and view them whenever they want. So our problem is defined as follows. Given the current user session, what videos should we recommend to the user next? Of course, the provider wants to engage the user more time in the website for reasons of advertisement and for fulfilling his viewing desires. There are several challenges in video recommendation, like the lifespan of video, which is short, which may be short. User sessions are usually anonymous and short, and also the interest of users may evolve fast over time. For this industrial project, we rely on well-known popular methods in session-based recommendations, like the session KNN algorithm, the GRU4Ec. We used as comparison pattern also the algorithm from Google proposed in IUI in 2010, and the well-known item-based collaborative filtering algorithm. The heart of our proposed method is the Markov chain, which is a stochastic process of possible events that satisfies the Markov property. And let's go to our motivating example. So in a real system, the server logs the interaction of users with the items, as can be seen here, for example, in session 7, which is still open, and it is running for user 2, based on the items I2 and I3 of this session, we can match with other items so that we can make item recommendations for user U2. As can be seen here, we have the chronologically ordered set of items, and we have also a sliding time window which can be used in order to validate the user click interactions based on the time that they happened. So we can be able to forget some data in case that they are obsolete or old. So the main method creates a transition probability matrix, which is a main step, based on the item interactions of users. So given a user's current session, SN, with item IM being the last item in this session, we can define the score for a recommendable item J by using this equation, which counts how many times a user viewed item J immediately after viewing item IM. The normalization term transforms the absolute count into a relative transition probability. So in our running example, based on this equation, we can compute the relevance of item 4 with item 6 as 0.5. Another important step of our approach is the creation of the recommendation list. As can be seen here, for a user U, we can compute the score for the candidate item J by using this equation, which consists of two main functions: the TPM function, which returns the similarity score for the two items, item I and item J, based on the transition probability matrix of the previous slide. And we have also the one function, which is an indicator function that is equal to 1 if the item J is present within the k nearest neighbor of item I and 0 otherwise. So the architecture of our approach consists of two modules. The first module is the profile updater, which updates the matrices and discards old information. And the second module is the recommender module, which uses the log history and the current session of the user in order to provide him the list of recommended items. Let's go to the experiments. So since this was an industrial project, we collaborated with the company over 3 years. And in the first year, in May 2018, we collected the offline data for our experiments, as can be seen here on the left figure. 50% of user sessions have only one video interaction. So 1 year later, in June 2019, we ran our live experiment, the A/B testing, and as can be seen here, on the right figure in this slide, users interact with 2 videos before leaving the service. Of course, this means that we managed to increase the length of the interactions of the user visit by factor of 2. So the number of interactions per session were in the offline data 3.6, and in the live experiments we resulted in 7.24, which was great for when it was announced by the company to us. One of the main important aspects in our experiments was the fact that we wanted to identify what is the future prediction, future horizon of our predictions. As can be seen from the top left figure in this slide, we are able to predict better when we try to predict the next 12 hours. We also try to identify the size of the sliding time window, and as can be seen from the bottom right figure, when the size of the sliding window is bigger than 18, the precision drops, which means that not all the past data is valuable for our recommendations. So we performed experiments with well-known methods in the area of session-based recommendation. We used as comparison partner the session Canyon algorithm, the GRU4Rec algorithm, and also the algorithm from Google from the IUI 2010 conference, and the well-known item-based collaborative filtering. In this result, we have the average precision at 5, where, as can be seen, the Markov chain transition probability matrix outperforms the other methods. And this is based on the fact that it is able to capture the notion of recency of users' interests. So this means that it is able to capture the short-term preferences of users, whereas other methods are not able to capture the latent associations among items within a session. The next step was to perform, the next year we performed experiments with the top 2 methods that we resulted from the offline experiments, which were the single ones, which were the item-based collaborative filtering and the transition probability matrix. So here in this diagram, we see the control group, which is the item-based collaborative filtering, and the test group, which is the transition probability matrix, the red line. And we computed the CTR, the click-through rate of the recommended videos, which calculated as the number of clicks on the recommended videos every time the user visits the UTV website. So as shown in this figure, the CTR in the test group is clearly higher than the CTR in the control group, and the transition probability matrix method improved the CTR upon the pre-existing collaborative item-based collaborative filtering method by 93.61% in this real-world experiment scenario. So, as far as the lessons learned, one of the main things that I would like to highlight is the time dimension, which is used in this evaluation or in this paper. So we use the frequential evaluation, which means that we performed several train test splits, time-oriented train test splits, and so this was very close to the real scenario of recommendations, and I don't think that we should continue to rely on simple static train test splits. Another important thing is that we were able to identify the short-term preferences of users, but also we could extend this method by trying to capture the long-term preferences, and this could be by trying to identify relations between items in different sessions. Of course, we need to compare this work with more state-of-the-art methods in order to validate our claims, to further validate our claims. As far as the precision versus the click-through rate for the offline and online valuation, in our case, the results are consistent and both of them can capture similar trends. Our method improved the CTR by up to 93%, and the user visit length by a factor of 2. The offline dataset may be biased, so this is something that we have to consider it as a future work. We should find ways to remove the sender or position bias from the data. And to improve predictions, we need to identify first the size of the future prediction horizon, and also the size of the sliding time window, which processes and validates the past data. So these were the presentation, and I would be glad to answer any question.
Okay, thank you. CS question. The first one is the sliding window based on time or number of interactions? The sliding window.
The time sliding window is based on
based
the time.
on the time or the number of interactions?
No, it is based on, yeah, it is based on time. So in this experiment, we used, let's say for the offline data experiment, we took the 2 weeks and we divide these 2 weeks in different time slots of, let's say, different time periods. And then we use them in order to run the frequential evaluation protocol, which is averages the data based on the time slot that these interactions belong to.
The second question is about the baseline methods. Have you tried recurrent neural networks, RNN, because it has recently been explored for sequential recommendation or session recommendation? RNN.
For the recurrent neural network, as a representative, we have the GRU4Rec algorithm, which is also an algorithm which tries to forget data by using the GRU unit. Yeah.
Okay, there are no other questions. I have one. I'm not very clear whether there are 2 TMF or 1 TMF transition probability matrix. There is one or there are 2 types, because you mentioned intersection and intersection.
Maybe it's not clear in this presentation, but the paper is written for the transition probability matrix based on the Markov chain. So this is the intra session transition probability matrix. And and an idea that could be as a future work for us would be, except of trying to identify the interactions between items inside the session, to try to extract association between intersession in the relations. So this was the...
I see. So in the future, maybe 2 types of TPM will be better, right? Okay. Another question is that I find that in your data, the length of the sessions are relatively short. For example, there are 3 or on average 3 or 7 items or 7 interactions on average for right. So in your solution, you focus on the local or the short-term preference dynamics. Is this because that in your applications that the session size are usually short? Because in some cases that the session size can be, or the sequence can be very long, right?
Yeah, of course, when you have a session, the average number of interactions per session is big. Then this means that the models are able to associate items more easier, and they can make predictions easier. In this case, where the size of the session is short, of course, for some cases it's difficult to identify associations. So this is a challenge for all algorithms. And
Right,
in
right,
our
I
case, yeah.
I see. Thank you. It's a more difficult problem. Okay. Thank you. Thank you for the presentation again. Now, due to time limitation, let's move to the fifth one. It's an industry talk. Our speaker is Markus Hess. He is a university assistant at Grace University of Technology. His talk is on the heterogeneous information needs in the job domain, a unified platform for student career. Let's welcome Markus.
Yeah, welcome to the industry talk on the heterogeneous information needs in a job domain, unified platform for student career. My name is Markus Reiters, data scientist at Telto. And in this talk, I'm going to share our experiences with solving the recommendation problem for university students. Specifically, I'm going to walk you through multiple considerations when developing a platform for students and how we at Telto tackle those problems. Let's first consider the job market from a recommender systems perspective. It's a difficult environment due to multiple factors. First, it's a multi-stakeholder system where the interests of both the employers and the employees need to be balanced. Additionally, the job market is very competitive, as only the best candidate or the best company will be chosen by either side respectively. As such, it can be seen as a matchmaking problem, where both parties must be satisfied for a successful match. Users on such platforms only perform a low amount of interactions that can be used for training. Moreover, users tend to leave the platform after they found a matching job altogether. Due to this, it is also important to consider the cold start problem, which is even more apparent. At Telto, we personalize the various aspects of the platform to overcome those hurdles, starting from the initial page. Telto is an Austrian career platform specifically tailored towards students and graduates. The platform itself is optimized for both desktop and mobile view. The latter is important as mobile applications appeal more to the younger generation. As you see on the left, we provide personalized job postings for users when they search for a job. And on the right, you also see cross-entity recommendations, where we recommend suitable articles based on the content of a given job posting. We found that our users, which are primarily students, have very different information needs. To satisfy those needs, we provide different types of content on our platform. Specifically, we provide job postings, company profiles, and career-related articles. Each type serves a different purpose and is of different relevance depending on the study progression. At the beginning of the studies, students search more for part-time jobs and study-specific career information. But when nearing graduation, their focus shifts towards relevant company information and full-time jobs. Additionally, we also need to deal with a periodically shifting demand as a result of the academic year, and handling both logged-in and anonymous users at the same time. Our solution uses a hybrid recommender system, which allows us to seamlessly integrate multiple algorithms into a platform for different use cases. For instance, we employ recommendations at multiple different locations, such as the main view and the sidebar. We employ a hybrid model that consists of well-established approaches like collaborative filtering and content-based filtering. But we also use more sophisticated methods to create embeddings like doc2vec and autoencoders. Our system is built upon a microservice architecture and uses the Apache Solr search engine, which allows us efficient retrieval and recommendations in real time. Here we see an example where we use the last interaction to find similar embeddings using doc2vec. Additionally, we improve the algorithms by incorporating cognitive-inspired recommendation approaches. For instance, one approach shown on the right uses a psychological model from human memory theory. We use it to create weighted embeddings that consider the recency and frequency of interactions of the user history, instead of using only the most recent interaction, as seen on the left. We also continuously perform E-B tests on our platform. Here, for instance, we saw that by using the base-level learning equation, we were able to improve the popularly used collaborative filtering for homepage recommendations. But on the details page, things are a little bit different. Here we saw that just considering the last item of the user's history gave us much better results. We investigated this by tuning the BLL equation and saw that the effects of recency have a greater influence for the user choice in context-dependent settings, as indicated by the higher time decay parameter D. As already said, we also focus on anonymous users. In this session-based scenario, we use autoencoders to infer embeddings for a particular session. This is then used in a KNN manner. If you want to know more about the specifics, we just published a UMI journal paper on this. While all of these provide effective recommendations, it takes a lot of fine-tuning for each use case to work well. Therefore, we were looking for a more generalized solution that can tackle the various different information needs, especially one that allows us to generate suitable cross-entity recommendations. In our latest effort, we adopted an approach called Item Concept Embeddings, or ICE for recommendations. The idea is to create an information network consisting of both items and words, as shown on the left, and transform them into the same latent space. As you see on the example on the right, from the original authors, the words Japan and Godzilla appear close to Godzilla movies. In our case, we first pre-trained word-to-vec models using the user and item vocabulary. For example, with the top TF-IDF words from the job description. We then create a heterogeneous information network consisting of items and words. We extract and link the concept words for each item. We then link each word to similar words, both from the item, shown in red, but also from words belonging to the user profile, shown in blue. We then learn the final embeddings of both items and words on the graph. For more information on the training procedure, refer to the ICE paper. Thus, our training procedure considers the network topology as well as the textual content. We store this once again in Apache Solr to allow for real-time recommendation generation and retrieval. With all this set up, we can utilize the network embeddings for 3 scenarios. Item to item, which recommends similar items. User to item, to create a personalized experience. And also query to item, where the input is a word. Thus, it can also be used for improving the search experience. While the example shows the procedure for jobs, we can use it regardless of the entity type. The important part is the overlap of the user vocabulary, which we built from user-created CVs on our platform. But the main focus of our approach is to provide cross-entity recommendations. We also found other use cases for it. This is especially true in terms of explainability. Since the model uses text as an integral feature, it makes it simple to show explanations for recommendations generated with ICE. For instance, if a job requires color and the user has Kotlin experience, we see that Java is the common denominator that is linked to both those concepts, and it can be shown as an explanation. Additionally, it also allows for several easy-to-implement use cases. For instance, we can also automatically generate complete content pages for suitable terms like deep learning, as seen on the left, or use it to extract the concept from a job posting to promote email subscriptions called search agents on our platform, as seen on the right. This work is the result of a research project comprising of the Telto parent company Moshpit, the Know Center, and the Graz University of Technology. Thank you for your attention, and I hope you enjoyed this presentation.
Okay, thank you, Markus, for the presentation. There are no live questions in yet. Let me ask first. Okay. Can you share with us something you think very important when developing a real system? For example, the techniques you're choosing, how to choose.
So I think one of the most takeaway messages is that it's really, you need to consider all the aspects of the different users, since although we tend to build upon that users are similar and recommend the similar items, like in the collaborative filtering scenario, but the user journey, the user experience needs to be really different in, I think, in many domains. So in for students, it's really hard since, like I said, depending on the study progression, it's very different what they actually are looking for on our platform.
Right. Okay. So I found in your slides you use Apache Solar, SOLR. Can you see more about this open source software used in your system?
So can you see more about Apache Solar?
Yeah. How is it used? What's the role of this?
Okay. Yeah. So we use it to as a backend to generate the recommendations. There we are specifically using the payload feature, since we are working mostly with embeddings, and this allows for really efficient retrieval of those embeddings. So this stores the index with the creates an index of the different vectors for each items. Thus, it's really quick to retrieve them.
Okay. There are no questions yet. Let me ask again another one. Why do you focus on the student job recommendation problem instead of other situations? For example, those are already working in companies.
Yeah, so this is as a result of the company history. So as I said, it's daughter company from the Moshpit, and they have the Studo mobile application, where there were, which is the most common university managing application in Austria. So most of the students use this, and then it was because of the domain knowledge that the company had, it was the logical decision to also create a career platform in the same area.
Okay, we have two live questions. First one is, how do you address multi-sided, that is reciprocal, two-sided, right? The job seeker and the job provider. The multi-sided nature of your platform. Do you consider the employer needs besides the students?
Yeah, not directly at the moment, since we found out anecdotally from our customers or from the companies that post on the platform that it's more, at least at the moment, it's more that the quality is really good from the applications, but they want more of it to have a greater choice. So currently we are focusing only on the user side. But of course, it's actually a bilateral recommendations matchmaking problem. Since one part is satisfied, it's more important. One part is satisfied, you need to focus more on the other part at the moment.
I see. Okay. Thank you. The second live question is, how slow makes SOAR adding a vector representation? It's about efficiency using vector representation and the software SOLR. So will it slow down your system using vector representation?
Yes, so Solar has the payload feature, as I mentioned. So this makes it actually really efficient. So
Right. Means the vector representation. You use dog to vector, right? Dog to vector.
Exactly, and then just store the vector as a payload in Solr.
Okay.
So we have there an add-on for the Solr search engine, which allows then the retrieval of the vectors in Solr. So really for the KNN, to retrieve the items in a KNN manner.
Okay, I found the industry paper is rather short. Will you provide, or will there be a long version of your paper so that the audience can learn more from your experience on developing such an interesting system? You know, the paper is short, right? Only 2 pages. Will be a long version.
Where they can learn more. So, as I mentioned during the talk, we already published several articles based on the work that we are doing at Telto. So they can read those longer versions on the specifics if they're interested. I can post it in the Q&A afterwards.
Yes, post it on Coba. That will be very helpful. Okay, thank you. Thank you, Markus, again for your presentation. It's very interesting. Okay, now let's move to the last talk. Our last speaker is Blaž Tos. He is a data scientist at Weike. His talk is balancing relevance and discovery to inspire customers in the Weike app. Let's welcome Blaž.
Hi, do you think that you are unique? I think you are, but we are also lazy. Why do I say this? Because in this conference, I have seen many presentations, and most of the people tend to use similar slides, including me. Same software, same style, same font. Why is this? Because the slide creator software recommends us the same things, and we are lazy enough to click on some of the first options. The influencer system, the recommender system influences us. We can look at recommender systems as influencer systems. Let's take a classical collaborative filtering approach as an example. In this case, the model is trained on user behavior data, so the users influence the model. And the model gives recommendations to the users, and they are clicking on some of the first options, so the model also influences the users. These two things amplify each other. Let's imagine that this recommender can potentially recommend 3 images, but in practice, it always recommends image A and image B. It never recommends the third image with the small chairs on top of each other. So image A and image B get popular because they are recommended. It will be a pattern in the data, and the recommender will exploit this pattern. But it never explores the third image with the small chairs on top of each other. If it would explore it, maybe it would find out that actually this image performs better than image A and image B, but we just simply don't know it. And it can lead to suboptimal recommendations. This is the shortcoming of classical collaborative filtering approaches, or generally classical recommender approaches. And I'm happy that also Ricardo in his keynote speech talked about this problem. And this is one of the problems that we keep trying to address in the IKEA app. Let me tell you more context about the IKEA app. I'm Balázs Tóth, data scientist at IKEA. I work on a new IKEA product called Inspiration Feed. The Inspiration Feed is part of the IKEA app. It's the main part of the IKEA app. You can see an example of the Inspiration Feed on the right side on my slide. The Inspiration Feed contains a set of inspirational or shoppable images. One inspirational image itself contains a set of IKEA products displayed in an atmospheric setting. We serve around 50 million recommendations daily. It's such a robust system. It's easy to get feedback about what is working in recommendations and what is not. IKEA tries to bring its home furnishing knowledge from the IKEA stores to the web and the app. And the inspiration feed is one of the initiatives that tries to contribute to this mission. The inspiration feed is one of the first things that the customers see on the IKEA app. So it needs to be explorative, like the IKEA stores. I can compare it to recommendations on a product page. In this case, we know more about the intention of the customer, so we display recommendations that are connected to that specific product. Here, in the inspiration feed, everything needs to be more explorative, but it also needs to be relevant, otherwise the customer loses interest. So we need two things here, relevancy and the element of surprise. To achieve this, we need to balance relevancy and discovery in a good way. So this is one of the problems we're trying to solve. Balance relevancy and discovery to inspire customers. And the other problem is that we want to avoid the bias in the recommender system. And it's the topic that I talked about in the introduction. To address these two problems, we use contextual bandits. More specifically, we use contextual bandits with batch learning from logged bandit feedback. We use counterfactual learning, and we make use of the counterfactual risk minimization principle. So I want to emphasize that we are not using multi-arm bandits. I see that it can be confusing from the questions yesterday. I can reflect to it. It's not multi-arm bandits. It's batch learning. We retrain the model daily on the batches. So we are not doing things on the fly online. So contextual bandits are a simplified version of reinforcement learning. The difference is that in contextual bandits, the reward is immediate and the states don't depend on previous states. In our setup, the context is user clickstream data. An action is when the recommender displays an image, and reward is generated when users click on images. Our policy is neural networks that uses embeddings of the input features. And we retrain this model daily, as I said before. And how do we do this exploration? We do it with the help of logged propensity scores. The basic idea is that if an image gets low propensity scores and at the same time it gets clicked, we try to put more weight on it to boost that image, to explore its potentials. And the intuition is coming from a statistics technique called inverse propensity weighting. It is used in experiments when some element of the population is underrepresented. For example, men above 100. And in this case, we just put more weight on the underrepresented samples to balance the underrepresentation. But how do we incorporate this to the training? We do it in the loss function. It is the heart of this approach. Here we try to optimize the expectation of reward under the new policy. Let me go through the notation. Delta is the reward function. It returns 1 if there is a click, 0 otherwise. X is the context, the clickstream history. Y is the action, displaying an inspiration image. And pi is the policy, the model. So pi theta is the new policy, the new model. And pi 0 is the old policy. It's coming from the logs, the propensity scores from the logs. So first, we compute the new propensity scores with pi theta, divide it with the old propensity scores from the logs, that's pi 0. And after, we multiply it with the reward function. So the reward function gives 1 if there is a click, 0 otherwise. So we're only dealing with the clicks. So after computing this, we're taking the average of it and maximize it. In practice, we take the negative of it and minimize it, since we work with gradient descent. I want to show you an illustration how the exploration phase of this system works. In this example, our context is viewing a chair, a specific chair that you see on my slide. And in this video, you will see that if a user clicks on this chair, which kind of recommendations will that user get? So which set of inspirational images she gets as a recommendation? And I will show that how the policy is changing day by day, and it explores and it learns from the exploration. So I want to show here, we want to illustrate that the model is, the system keeps learning. So here you see the first day. You see some images with that chair. Second day, you see even more images with that specific chair. And along as we go forth, there are more and more exploration, and the system learns from this exploration. I'm proud that we have built a powerful recommender system for the IKEA app. We ran an A/B test. The A version was a classical collaborative filtering approach, and the B version were contextual bandits. We ran it for a week. There were around 1 million unique visitors involved in the test, and we ran it in the 6 biggest IKEA markets. The 6 countries where IKEA has the biggest markets. And the results showed 20% increase in click-through rate for the contextual bandits. And in our case, the click-through rate was the measure of success. The shortcoming of this approach that it only does this with click. So it doesn't explore images that were never got clicked. It could be a start with the cold start of inspiration images. To solve this issue, we have another panel when there are only the new inspiration images are displayed. Initially, we assign some propensity scores to them, and as they get clicked, they naturally blend into the training data. We also want to experiment with the loss function, and among others, we want to use images as input to the neural networks. I summarize my talk. Exploration is essential for a good recommender. And if there is only one message that you can take away with you, I hope it will be this one, and it will help you. We used contextual bandits in the IKEA app, and it improved recommendation quality and variety. We ran an A/B test, and it showed 20% increase for the contextual bandits. Thank you for your attention. We can proceed to the questions.
Okay, thanks for the presentation. Thanks for the presentation. We have live questions in. First one is, can the reward function be created to include a long-term reward like user retention or a potential purchase, which might not be known instantly? Long-term reward.
Yes, so that's the next step. Right now, we optimize the model for click-through rate. And that could be the next step to, for example, optimize it for revenue or something else. But that was our first step, to optimize it for click-through rate. It was the easiest thing to do.
Okay,
and I think
click-through rate.
Sorry?
You only measure the click-through rate, not something like conversion rate?
Yes, only click-through rate.
Okay. Okay. The second question, probably in the future, long-term reward may be a very good issue to be addressed. The second question is, do you consider the clicked items position, the position of the clicked items?
No.
In the location or position? No.
We don't.
Is the reason, is that because of the small screen on IKEA app?
No, we just, probably it's a good idea. We just don't do it. We treat them equally.
Okay, because there is a position bias in counterfactual learning or some related works, right? Okay, the third question is, what are the ideas to build individual user personalization in this approach? Is it personalized?
Yes, it is personalized.
Right, okay, so of course.
So
okay.
it's personalized with...
yes.
So it's like the neural networks itself, the model is doing the personalization.
Okay.
So,
okay,
and should I continue with the answer?
Okay, please continue.
So in this case, user is defined by her clickstream history. So if user A clicks on a set of items and user B is also clicking on the same set of items, we treat them equally. So they will get the same recommendations. So that's our personalization there. So you are your clickstream history in this system.
In your study, do you observe some reduction in clicks caused by exploration? So when you do exploration, will there be some loss in clicks? Some reduction in clicks?
No. So we do the exploration every day.
Okay.
And we run the A/B test and it showed the increase in click-through rate actually.
Okay, so exploration is always helpful in your application, right?
Yes, so we are doing targeted exploration. We don't do random exploration. So if we would do random exploration, for example, only on some percentage of the data, I would expect that there is some decrease. But here, we don't have decrease. I cannot hear you. Sorry, I still cannot hear you.
Yeah, I think Professor Pan is offline. Okay. So do you think we can conclude the section?
Yes. Absolutely.
Okay. Okay. Thank you for the speaker. Thank you for all the speakers again, and thank you for attending the sessions. Please check out our social activities over the next hours. See you around. Okay, thank you. Have a good day.